Hello everyone, this is Dr. Lennon, and I just want to go over a few of the related rates examples on the homework. Again, remember the idea here is to basically write down some formula that relates the variables. Then we take the derivative implicitly, and then we plug in all the known values to figure out for the rate that is in question. So the fact that this is a question about how the relates depend upon each other is the indication that we need to use the derivative. Remember, regular variables are just going to be a measurement of some standard value, whereas a derivative is going to give you a measurement of the rate of change of that value at a particular time. So in this problem, we have the length of a rectangle is increasing at 3 centimeters per second, and its width is also increasing at 7 centimeters per second. So the first thing we want to do here is draw some type of rectangle and just label the two sides. So let's call the length, let's say that's x for this problem, the horizontal component, and maybe the width is y, and I'm just labeling that so it's the vertical component. So what are they giving us right there? They're giving us the rate of change of both x and y. So we're saying, okay, well, our dx dt, so that's the rate of change of the length, is 3, and dy dt, the rate of change of the width, that is 7. So what do they want? Well, they want to know how fast the area is increasing. So they want to know what is dA dt at a particular time. So they want to know when the length, which we labeled x, is equal to 7, and the width, y, is equal to 4. Okay, so what are we going to use here? Well, we're going to use our area formula. Area is equal to x times y. So we want to take the derivative and we want to take it implicitly. We don't have a way that the variables actually are related depending on each other, but that's okay. We can go ahead and think of x and y as separate functions of this third variable t, and we can use the product rule. So basically our dA dt, so that's the left side. The derivative of a would normally just be 1, but since we're thinking of a as a variable of this independent function t, we're going to use dA dt. So then u, so we're using the product rule here. So the product rule for x, y, if we call u x and v y, then u prime will be dx dt, and v prime will be dy dt. So we get our derivative of that side would be x times dy dt plus y times dx dt. So that's what we replace on the right-hand side over here. So this is the use of the product rule for derivatives. So we have x dy dt plus y dx dt. And what we want to do is just plug in the known information. So dA dt here is given by 7 times 7 plus y is equal to 4, and dx dt is equal to 3. So we get 49 plus 12, which is 61. So the rate of change of the area at that particular time is 61, and what were the units for this problem? Centimeters per second, so area is going to be centimeters squared, so the rate of change of the area is 61 centimeters squared per second. So that's our answer to this problem right here. And again, that rate of change of the area is going to fluctuate depending on the particular values of x and y that we include. All right, so let's go ahead and go to the next example problem. So let me put this thing down here. So I wanted to insert, I've taken screenshots of the pictures, so I'm just going to include those. So the next one, and let's try to resize that again. This one is essentially similar to one of the Pythagorean example word problems we did, but it just gives us all of the values. So we don't have it in the context of a particular problem. And one thing to note, x, y, and z are positive functions, so that's going to be similar to the word problems. So if we end up with some answer like x squared equals 9, we don't have to worry about plus or minus the square root. We can just take the positive square root. So we have the equation that relates the variable z squared equals x squared plus y squared, and they want us to find a particular dz dt. So when you take the derivative implicitly, we get 2z times dz dt equals 2x times dx dt plus 2y times dy dt. So then, again, to simplify this a bit, you can divide both sides of the equation by 2. And this simplifies to z dz dt equals x dx dt plus y dy dt. And we can go ahead and just plug in the values that they give us. So we know everything except for z and dz dt. So they give us two particular x values, x equals 8 and y equals 15. So let's go down here and find z when x equals 8 and y equals 15. So we get that z squared is 64 plus 225. So that is 289. So z squared is 289. So actually it turns out if you use the square root, that the square root of 289 is exactly 17. So to plug in the known values, we can replace z here by 17. dz dt is the real thing we're trying to find in this equation. We're given that x is 8, dx dt is 3, y is 15, and dy dt is 2. So we end up with 17 times this dz dt equals 24 plus 30, which is 54. So divide both sides by 17. So dz dt turns out to be just 54 over 17. So that would be the answer to this problem. So this works the same as one of those triangle problems that come up quite a bit. The two examples we looked at previously, we had two boats traveling and looking at the distance between them, and then we also had one where a ladder was falling. So the Pythagorean theorem comes up quite a bit in these word problems. All right, so let's go ahead and look at the very last one, which is another Pythagorean theorem one, but it is in the context of a word problem. So let's go ahead and insert that. Let me get the cursor down here in a good spot first. Oops. So let's go ahead and insert that picture. So in this one we have two cars moving from the same point. One is traveling south at 48 miles per hour and the other is traveling west at 20 miles per hour. At what rate is the distance between the cars increasing 2 hours later? So this is going to be very similar to the previous problem, but actually only two sides are going to be changing. No, all three sides of the triangle will be changing, so it will be very similar. So let's start with our triangle. We have one car traveling southbound, and then the other one's west, so maybe I should give myself a little more room. You could really write this so they're traveling north and east if you wanted to. The problem wouldn't change any different in terms of the rate at which the distance between them would increase. Okay, so if we call this side x, this side y, then the distance between them we could call z. So it would pretty much mirror the previous problem. So then the way that the variables are related would be x squared plus y squared equals z squared. And then we know the related rates, the implicit differentiation would end up coming out to x times dx dt plus y times dy dt equals z times dz dt. There would be 2's there and an intermediate step, but we saw that we could divide both sides by 2 and everything would go away. So basically, what is the given information? The given information is the car traveling west is your x variable, so dx dt is equal to 20, and the car traveling south is dy dt, so dy dt is equal to 48 in this problem. So the other thing we need to do, again, is figure out the value of z at the particular time. Okay, so actually what's going on here is they're asking what is the rate of change 2 hours later. So 2 hours later, so at t equals 2 is the one reason this problem is maybe a little bit different. X would equal twice its speed since they start moving from the same point. So x would be 2 times 20, 2 times its rate of change, which is 40. Right? If you're traveling 20 miles per hour for 2 hours, your displacement would be 40 miles. And y would be 2 times 48, which would come out to 96 miles. So now we want to figure out z, and we can do that with the Pythagorean theorem. So z squared is going to be 40 squared plus 96 squared. So our value for z squared is, let's go ahead and appeal to the calculator. 40 squared plus 96 squared comes out to 10,816. So z is going to be the square root of that number. And let's see if that comes out as a good value or not. Yeah, it comes out to exactly 104. A lot of times these textbook problems do. So now we have everything we need to plug in to our related rates equation. Again, x is equal to 40, dx dt is equal to 20, y is equal to 96 here, dy dt was 48, z we just found was 104, and dz dt is the rate that we're trying to solve for. So let's go ahead and plug those values in. So we end up with 5,408 as the left side of the equation, and then 104 dz dt on the other side. So dz dt is going to equal 5,000. So this is multiplied, so we're dividing by 104, so we get 5408 over 104. And that comes out to exactly 52. So the rate of change between the two cars at that moment in time is 52 miles per hour. So that is our answer for the third question. So I believe that was number 8 on the homework. All right, so if you have any additional questions, please let me know. Otherwise, have a nice weekend, and I will talk to you soon.